Hi, Amanda.
Huh. Hey, I just sent you a text.
I can't see anything, but I can see you. I just was I see that it's recording, but that it says I was the first person to join.
Oh, yeah, I see that it says Brian started recording.
Yes, I see that too. He's lurking somewhere.
In the background.
Well, we both ended up at the same place, so at least that's a good sign.
But we both happen to make the same mistake.
Well, what's that old saying? Don't follow me, I'm lost.
Yeah. Let's see.
Did you have any issues with your enrollment this quarter, Amanda?
No, I have not.
Okay.
Why?
Well, it's telling me I enrolled as normal, and it gave me the tuition waiver, and then I got an email that said I wasn't registered, and then I got one that said I was dropped from one of my classes for non-payment, and it's like, well, I just paid you a crap ton of money.
Well, that's frustrating.
Well, I'll just call admissions tomorrow. I mean, it's probably just some stupid glitch, but I just don't want to get hung up. Hi, Jackson.
Hello, how are you all?
Good, how are you?
Oh, not too shabby.
Yeah, how was your little break?
Oh, wonderful. Just so wonderful.
Is that a little sarcasm we hear there?
Oh, no, absolutely not. It was great.
Our census exploded, so my break consisted of lots of overtime.
I don't know if that's a bad thing.
No, but I had a 15 sim week. That was fun.
That's a lot. Yeah, I right now am the only dosimetrist at my site.
Good Lord, woman.
Yeah.
Well, that gives you a lot of time to practice, hon.
Yeah, honestly. My physicists have been planning their little butts off.
I looked it up on Google, and I don't know if this little factoid is true, but there are only 4,300 dosimetrists in the entire world.
So what was interesting is the last time Bobby was in, he was on a meeting with the MDCB and I don't remember who else. It was two different groups. And they were talking about the extreme shortage that they're going to be experiencing within like the next couple of years. And he said, I don't think that hospitals understand like the severity of the shortage that the field is going to go through. So I just thought it was interesting information.
It is, and that sort of makes me rub my little hands together and say, how about a raise?
Yeah, exactly. Me too.
Did he say why there was going to be a severe shortage, or is it just retirement, attrition, or?
Yeah, and I don't think there's a whole lot of programs that are around. And the programs that are, there's issues with like keeping accreditation or something like that. So they can't get students out fast enough. It all has to do with the requirement change too, and requiring people to actually sit for the boards and go through a certified program.
Yeah, I mean, our previous dosimetrist had been a therapist who was just trained in-house.
Yeah, and actually that's what my preceptor was trained in-house. Yeah, I think hospitals used to do a lot of that, but unfortunately that's gone.
Well, hospitals don't understand a lot about radiation oncology. We are in the throes, I should say, I was going to say midst, but throes of switching over to Epic.
Oh, yeah.
And Epic is not like Mosaic at all.
I don't know that Epic makes friends with really any other kind of system.
Well, Jamie warned me. Hi, Jamie. Hi, Allison.
Hey, Sarah. Yes, Epic and Mosaic, they're totally my best friends.
Your sarcasm is showing, sweetie.
She sounds like Jackson did.
Yes, exactly. Except Jackson was serious. Obviously, maybe I just have my sarcasm filter turned up on high and everything I hear is sarcastic.
Oh no, I was definitely being sarcastic.
Yeah, I am not enjoying Epic. But you should hear our physicist. He's ready to pull his hair out. One of our IT guys has called it, Jason has chosen a hill to die on, because he is so upset about the way documentation is handled in Epic. And something as simple as putting out, exporting a plan with the RadCalc document separate, it is not allowing him to do more than one plan into Epic per day per patient. And that's just not going to work. And then it won't name any of the plans, so you don't know what they are. They're just called generic care plans.
Nice. We haven't been able to figure out how to bill for a CT since we went live months ago. So that's fun.
Oh, yeah. We're talking Epic, Brian. I don't know if you've had to deal with that.
Fortunately, I haven't. Can you guys hear me okay?
Yes.
I've been in a couple of places where they've used Epic, but it's always been far enough removed from what I do that I never had to touch it.
You're a lucky man.
Yeah, I've heard rumors and grumblings and stuff, but actually, I think the center I'm at now here in Mount Vernon uses Epic, but the records that they keep there don't really cross over to physics, so I never have to get into it.
Are you at Providence by any chance? You in one of the Providence hospitals?
I don't think Mount Vernon is a Providence center. I could be wrong, but I'm just a contractor, so I don't worry about that too much.
Okay, that's why. You are a lucky man.
I'm insulated. I'm pretty insulated from most everything. It's kind of nice. I think it's actually clinically useful too, because a physicist kind of needs to be independent to be able to tell people that's not a good idea. And if you're an employee and your boss is, the same person that's telling you you have to do things this way and it's not safe, and it's a little harder to push back and say, I'm sorry, that's not safe.
Well, yes, being able to stay out of that kind of politics is always a good thing.
Yeah.
I've never experienced it like totally firsthand, but I've seen it in the hospital. People get very stubborn and territorial.
Right. All right. Well, the start time has come and gone. I want to say there's probably a couple more, but we are recording, so I think we'll be all right to go ahead and start. I assume everybody's still okay with recording class. If you're not, you're welcome to message me. Let me actually, to that point, let me open the chat so I can see if you guys have anything to say non-verbally. I see that you're all not on video, and that's fine. We were actually just instructed as teachers to let you guys know that video is not required. There are some equity issues, I guess, with requiring people to be on video. Probably because if I saw your Britney Spears poster in the background, then I would judge you and probably give you worst grade or maybe a better grade. I don't know. Is Britney Spears a positive or a negative these days?
It just depends on which side of the conservatorship debate you're on, I guess.
If you're a Free Britney fan, then yeah. Anyway, so let me actually go ahead and share my screen. And I've got these meetings just automatically recording, so you shouldn't need to remind me, and I shouldn't forget.
It started recording the minute I joined.
Yeah, I set it up that way because I remember last time worrying every time that I would forget to record it. So I just set it up to automatically record. So if I share my desktop, and if I remember correctly, if I go full screen, I can't see the chat, so I won't do that. Let's see. One of these days, I'll find a video conferencing solution that does everything I want it to do, and then we'll all be happy. All right, I can see the chat. I can see the screen. Is that big enough for you guys to read? We'll go to a small one. Is that big enough for you guys to read?
Yeah, looks good to me.
Okay.
Yeah, I'm okay with it.
I can't, I mean, I'm not seeing full screen. I'm just seeing.
Right. I don't, if I go full screen, then I can't see the chat because I'm sharing my whole desktop. And I don't think, yeah. Anyway, actually, let me try something. Let me go back here and just share. Just share the PowerPoint. All right, now if I go full screen with the PowerPoint, can you guys see, what do you guys see now? Just the PowerPoint?
PowerPoint, and I see a gray square or gray rectangle off to the right.
Is it interfering with the picture?
Yeah. Yes.
Yeah. Okay. That's kind of what I thought would happen. So we can't do that. I thought maybe if I just shared PowerPoint, then it would let me see the chat window without obstructing your view, but I guess not. So we'll do it the same way we did before and deal with, let's see, actually, all right, so let's share the whole desktop. And that'll be okay. I can probably, what can I do? I can probably get rid of that. That'll make it a little better. Okay. Welcome to DOSI 331. This is the first time I've taught this course, so I'll be about a half step ahead of you guys, maybe a quarter of a step. The book is the same one we used for physics, Physics of Radiation Therapy by Khan, and older versions, latest version is version 6, I think. 6th edition, older versions are okay. Since Khan didn't actually publish any problem sets, which is kind of mean of him. But I do have a question for you guys about the Khan planning book. Since this course has a little more focus in the planning realm, I thought it'd be nice to be able to use some stuff from Khan radiation therapy planning. Does everybody have that or have access to it?
Yes.
Okay.
Felita required it from one of her classes. I don't know if other people bought it, but I know I have it.
That's what I thought, but it had been used in a couple of other classes, so I thought it might be safe. But if anybody doesn't have it or has sold it back or something and doesn't have access to that, let me know. Otherwise, I won't use it as a main textbook, but just as kind of a supplementary textbook. So as long as you guys all have access to that, then I'll go ahead and pull from that a little bit here and there. Okay. Contacting me, there's my cell phone number. And if you guys want to text me just in case your cell numbers have changed, that way, if I have an emergency and class is canceled, I can text you. Same as last time, I probably will very rarely, if ever, use that, but it's nice to have just in case. Another one caveat there is when I'm at work, my cell phone gets really, really poor reception. So during the hours of 8 o'clock to 5, you might not be able to get a hold of me through my cell phone number. And so if you have time-sensitive issue that you need to get a hold of me, then there's my office number. I am working on getting my cell phone service switched over to somebody that actually has good reception here in Mount Vernon, but that hasn't happened yet. So there's an alternative. The lecture schedule is currently 7 to 8:30 on Wednesdays. And hopefully that works for everybody. If there's a preference by a majority of the class, it wouldn't bother me to switch to like 6 to 7:30 or something, but I figure a lot of you are working and probably helps to have a little extra time in the evening to prep for class. And then hopefully you're all aware, but I'll just remind you that Bellevue College has a COVID vaccination policy that faculty and students are required to either be vaccinated and submit proof of vaccination or to fill out a waiver of some sort. So if you haven't seen that, haven't done that, I think it's due by October 4th or 5th or something like that. So fairly soon. So just keep an eye on that if you haven't already done that. And are there any other questions or just kind of general housekeeping items that I've missed? Other than my terrible lighting, I need to get some extra lights for my room. Okay. So here are the course outcomes for this course as published on the website. We're going to look at when we would use particle beams, electrons, protons. So clinical situations when you would use these. We're going to look at isodose lines, isodose patterns for different types of particle beams. We're going to look at the effects of different beam modifications on particle beam therapy, risks and benefits of particle beams versus other types of treatments. We'll define therapeutic range, which is kind of the first thing you'll look to when picking an electron energy. We'll define the Bragg peak for protons and for other heavy charged particles and discuss the importance of that. We'll talk about MU settings for electron prescriptions. That's going to be the primary thing that we'll do calculations on, since that's really the only thing you'll ever do a hand calc for in the clinic. Calculate dose to a point in an electron field. That's just the opposite of an MU calculation. Define the role of virtual source in MU calculations. Choose energy and field size for a clinical situation. Clinical issues for field matching. Electron to electron and electron to photon fields for abutting fields. And discuss the roles of special utilization of electron beams for electron arc, total skin, and if we have time, we might also look at intra-op electrons. But this, since we're only meeting once a week, pacing and time is going to be a big factor. Okay. So today, and let me actually go real quick to the calendar. So today we'll start with just an overview, kind of a review of particle interactions. And then we've got 3 more weeks after that to do, basically we'll be doing electrons for the next 3 weeks. And then we'll do, oh, this is my Outlook calendar, not my. Let's go to the Canvas calendar instead. There we go. So review of particle interactions, and then we'll do electrons, hand calcs, and then special electron treatments like total skin. And then we'll do midterm review, we'll do a midterm, and then we'll go into protons and neutrons and any other special topics we can get through. And then that'll be it. Once a week lecture is going to be, it's going to be tight for me anyway. I like a little extra space, but it's only a 3-credit course, so I can't kill you guys too much. So that's kind of the overall schedule. Final is scheduled for the Wednesday of finals week, same day as our lecture. Okay. So basically, if you want to go back and look at Con Physics book, this is coming pretty much from chapters 3 and 5. We're just going to do a conceptual review, no calculations. Looking at ionization, looking at photon beam attenuation, interaction of photons with matter, and then interactions of charged particles. And kind of the reason I go ahead and do photon beam stuff in the charged particle course is just to help you differentiate between the two, because a lot of these interactions sort of get blurred together over time. So just to kind of differentiate the different interactions, photons versus electrons versus protons. So they're all kind of clear in your head before we start. So ionization is a general term. It just means a neutral atom is acquiring a charge. In general, for this class, we're almost always talking about losing an electron, becoming positively charged. And the electron gets knocked out by some form of radiation. And so that happens by two main categories of radiation: those that are directly ionizing and those that are indirectly ionizing. The directly ionizing radiation are the charged particles. They can interact directly with electrons. So electrons obviously can interact with electrons. Protons, alphas can come in and interact directly with an electron, knock it off of an atom, and cause an ionization. And then indirectly ionizing radiation is uncharged particles, so neutrons, photons. They cause interactions that then the secondary interaction is what causes the ionization, right? Or it's not a direct interaction with an electron. It might be an interaction with the atom as a whole, or with a nucleus producing energy that then ionizes. Now, a quick question for you guys: why do we care about ionization with regards to cancer treatment? So forget all the stuff about production of therapeutic beams. Obviously, ionization plays a big role there, but what about cancer treatment? What's the purpose of ionization in killing tumors?
One of the things it does is it reacts with water to create hydrogen peroxide, which kills cells, especially cancer cells, because they can't repair from hydrogen peroxide production.
Yeah. And
also,
then
DNA damage.
Yep, there's the other one. So DNA is another target, right? So so that's why we care about ionizing radiation, right? And if it's not ionizing radiation, then it doesn't have the power to do any of the stuff that we want it to do in treating cancer. Okay, so directly ionizing radiation those are the charged particles. Those are the ones we're going to talk about the most this term. And because these charged particles can interact with any electron they see, they tend to lose energy in small amounts. They tend to interact a lot. So lots of small interactions rather than one or two big interactions. Although, if you do get a big interaction, then sometimes instead of just ionizing an electron that goes off with low energy and then gets absorbed again, the secondary electron can have enough energy to go off and create its own ionization, go off and ionize other electrons, and that's a delta ray. And then if the particle coming in doesn't interact strongly enough to eject the electron, it might just excite the electron, and that electron would then go up to a higher energy level, fall back down, emit characteristic X-ray. Okay. For photon beams, we worry about fluence, the number of photons per cross-section area. We worry about the fluence rate and the energy, and then multiply that by average energy, and you get kind of an energy fluence. And that's just to talk about, you know, kind of what do you start with as far as how many photons are incident on your patient or incident on your shielding, and then it attenuates from there. That's the e to the minus mu x, the exponential decay formula that we use for a bunch of different things. And as the photon goes through thicker and thicker slices of material, the incident photon flux, or the incident photon fluence, will attenuate, and so there you'll have less coming through because they either got absorbed or they got scattered in the material. And then because of that, you can talk about half value layers, where after a certain thickness of material, you only have half as many electrons, or half as many photons in your beam as you started with. A quick reminder, if you remember, when we talked about production of photon beams in an accelerator, when you bash electrons into a tungsten target, you don't get a single energy coming out, you get a broad spectrum of energies of photons coming out. And so the first half value layer is going to be more effective because it's really easy to attenuate a lot of the low energy portions of the spectrum coming out of that accelerator. And then once you've attenuated all of the easy ones plus some of the hard ones, then the rest of them are kind of all sort of the same. You can think of the second and third half value layers as being the same. They're probably not exactly the same, but so the first 50% of the beam is the easiest to attenuate, and then to knock it down by another 50%, and then another 50%. It's going to be a little harder each time because the beam gets harder each time, right? Harder meaning the average energy is higher. So the reason all of this is happening, what's going on inside there, we've got a couple of different interactions. There's Compton interaction that is the most important for our therapy beams. And then the other interactions that we can talk about that we'll see some of in other areas of radiation therapy: coherent scattering, not so much; photoelectric effect, Compton scattering, pair production, photo disintegration, and triplet production. Really, photoelectric and Compton are the two that you want to really know well conceptually, because those are the two main ones. Photoelectric tends to be the effect that we want for imaging. Compton scattering is the one we want for therapy. So for coherent scattering, your photon comes in, interacts with an electron, or the electron cloud in the atom. Those aren't really two different things. That's just two different ways to say the same thing. And then what happens is there's a interaction. You get an oscillation at the same frequency as the photon coming in, and then there's a photon that comes out at the same frequency, but in a different direction. So there's really no change in energy of the incident photon, which means it's probably not all that useful for anything that we're worried about. Probability increases with Z, the atomic number, and yeah, not important. It's really for very low energy photons, and so it tends to be a low probability interaction for even for the imaging beams that we deal with. This is just a diagram of that. You're interacting with electrons in the orbitals, not with the nucleus, and it increases with Z and increases as energy decreases. So the lowest energy photons are the ones that tend to have this coherent scattering. Photoelectric is a little more important. This is a full absorption of the photon. And it almost always happens with the K-shell. The K-shell only has 2 electrons. That's the hydrogen and helium orbital for the electrons. And so you come in with a photon, it hits the K-shell, and it gets absorbed. In order to be absorbed, that photon has to have enough energy to eject an electron from the K-shell. So it has to have an energy that's equal to or greater than the binding energy of the electron in that K-shell. The K-shell is the one that has the highest binding energy because it's closest to the nucleus. Oh, there we are, closest to the nucleus, right? And the electron gets ejected. So photon comes in, gets absorbed, electron gets ejected. So there's an ionization event, unlike the coherent scattering, which doesn't really ionize. And then any excess energy is given to the electron. So we don't have any photons coming out, just the electron with whatever extra energy was left over after overcoming the binding energy to eject it. And then that hole that gets left in the electron orbital is filled by an electron that's at a higher orbital or a lower energy. And then that process will emit a photon. Right, so this photon here is not directly from the interaction, but it's a secondary effect. So we get this characteristic X-ray that comes out. We're dealing mostly with low atomic number material, carbon, oxygen, hydrogen. That's what we're all made of. A little bit of calcium, right? And so characteristic radiation tends to be low energy. So the bigger the atom, the higher the binding energy of that K shell. So there are some examples in the low single-digit keV range for those characteristic X-rays. So mostly made up of water. That's why when I go do my data collection for a new planning system, I get out a water tank and measure in water. So that's what most people are mostly made of. And so there's your K-shell binding energies, 540 EV, which is pretty small compared to the energies that we're dealing with, even in your low energy imaging beams, 100 keV, quite a bit larger than the binding energy of your K shell for water. So photon comes in. Ejects an electron. This is just to run the numbers so that the stuff that I just said makes maybe a little more sense. If you have 200 keV photon coming in, it's going to lose 0.5, 540 EV to break that electron loose. And so it'll be, so that electron that comes out is going to have 199.5 keV of energy in motion, energy of motion, sorry. And then outer shell electron or a free electron will come in and fill that vacancy, and you'll get a 54.54 keV, 540 EV characteristic X-ray. Let me just skip, let's see. Yeah. So when we talk about characteristic X-rays, there'll be little spikes in a spectrum. So you might have a bunch of photons coming off in a nice smooth spectrum, but then you'll have these spikes here where the characteristic X-rays are because they're single energy. And photoelectric effect, yeah, so that's kind of the basic interaction there. 90 degrees. You probably don't need to worry too much about what direction the electrons are ejected at. Other than it's sort of nice to know that high energy electrons tend to be more forward biased. That's sort of a good thing to remember for a couple of different things. So your low energy imaging X-rays are kind of this, right? So 90 degree no, never mind. That's not that important. Photoelectric. So the energy dependence is 1 over E cubed, which is very strong. So it is strongly dependent on energy, and as energy increases, this photoelectric effect starts to go away rapidly. And then it's also strongly dependent on Z. Since photoelectric effect is our imaging interaction, why is it nice that it's strongly dependent on Z?
Helps show different densities.
Right, so specifically what types of things show up really well because they have higher Z in the body?
Bone, calcium.
Yeah. So bones show up really nice because we're using the photoelectric effect to image, and calcium is higher Z than most of the other stuff in the body, gives you really high contrast, right? If you look at MV images, the bones are kind of washed out. They don't pop like a KV image, right? Which is because photoelectric effect is no longer dominant at the higher energies. And you can kind of see the energy range that we're talking about here, which is your imaging range, right? 60 to 100 keV. That's sort of the area in which you start getting less and less photoelectric effect. And so even at the imaging energies that we use for planar and CT images, the photoelectric effect is already starting to diminish quite a bit. For high energy photons, you have to go clear up to lead to keep any photoelectric effect going. Water, it's already basically zero by the time you get to 100. This would be 100 keV, right? In the MEV range, there's not much going on in water. It's all going to be Compton scatter. You'll still have some photoelectric effect for lead, so you could expect to see pretty good contrast for lead in an MV beam, although I'm not sure why that would ever be useful. Most of you probably aren't putting lead coils in prostates, although some of the other stuff. What are you using? You're using gold. Do you have any other? Does anybody know what else you've used for seeds, marker seeds for imaging, for MV imaging? I know they make gold coils. I know they make I don't know, probably stainless steel, but be interesting to. I haven't looked deeply into what other materials they use for those. And then those characteristic X-rays, that's that secondary interaction. And those are the energies. You can actually tell if you look at a spectrum coming out, and I didn't tell you it was lead, if you knew exactly what energy those characteristic X-rays were at, you could tell me what the material was. So that's why it's called characteristic, because the first use that anyone put those specific single energy X-rays to was to figure out what material they were looking at. Compton's a little more interesting for us because this is what we use clinically. We send MV photon beams into a patient, and what we want is Compton interaction causing the ionizations. What we don't want is Compton interaction during our imaging, because all it does is scatter the radiation. Scattered radiation is not good for imaging, right? You want it to either go straight through or get absorbed. That gives you a nice image. Anything that's scattered doesn't give you any information about where it came from, and so it's just fog on the film. The nice thing about Compton interaction is it is not dependent on atomic number. So when you treat your patient, you don't have to worry about overdosing the bone, because it's going to treat bone the same way that it treats fat, the same way that it treats muscle, the same way that it treats any other tissue in the body. You'll get a little bit extra dose deposition in bone just because bone is denser, at least around the outside, but not nearly what it would be if this was more like a if it was a z squared or a z cubed interaction like photoelectric effect, then your bones would be getting just ridiculous amounts of dose. So that's kind of nice. So for Compton interaction, it's not going to interact with that K-shell electron. It's going to interact with one of the outer electrons, one of the more loosely held electrons. And as it comes in, it's going to transfer just a portion of the incident energy. So instead of being completely absorbed, it transfers some of its energy to the electron. The electron gets ionized, comes out with some kinetic energy, kind of a random amount. And then the photon also leaves with whatever energy is left over. So this is just the diagram. We're going to interact with an outside electron now. And then we have two particles coming out. We have the ejected electron, we have the scattered photon. And the photon scattering angle is dependent on how much of its energy it gives to the electron. So if it gives up most of its energy to the electron, then it'll be scattered at a bigger angle, sometimes even backwards. If it doesn't give as much energy to the electron, and this is just random chance, then it'll be scattered more forward. And then because there's an ionization, you're also going to get an electron coming in, filling the hole, and you'll get a characteristic X-ray coming off. These are such low energy that you don't see them unless you're really, really looking for them, and they're not significant in any kind of therapeutic sense. So Compton interaction does depend on energy. So as energy increases, Compton interaction probability goes down, but it's only 1/e. It's just a linear relation, unlike the e cubed, 1/e cubed, or 1/e squared, like some of the others. And so it's fairly weakly energy dependent. That means that gives you kind of a broad range of energies where Compton interaction is still dominant, which is one of the reasons why it's so significant for us, because most of the energies that we deal with, Compton interaction is going to be dominant. And partly that's because it's not too dependent on energy. It's independent of atomic number. We already talked about that. This is a graph of that probability that we just talked about as far as energy, 1/e. And so as you increase energy, the probability of Compton interaction goes down, but you're still looking at fairly high probabilities as you go up in energy. 50% probability is still pretty darn high, right? And 20% probability, still a pretty good probability of interaction. For hydrogen, things are just a little bit different. And so we graph everything else separately. Hydrogen has kind of a factor of 2 difference from almost all the other elements with respect to its electron density, with respect to its some of the other factors that go into this. But this graph by itself isn't as fun as the one we get to a little later, where we put all of the interactions together. But clear up to, what's that, 20 MeV, you're still getting Compton interaction. So that's just a rehash of the photoelectric effect graph. And then there's the Compton effect, the Compton interaction on top of it. So you can see, even though on the previous graph it kind of looked like the Compton interactions were low probability, when you compare it to the probabilities of the photoelectric effect at the same energies, you can see that that's pretty high probability interaction all the way up, to the higher energies. It's always good to have a comparison for scale. Okay, third interaction that sort of comes into play for high energy photon beams is pair production. And it has to be greater than 1.02 MeV. And that's because pair production is the creation from energy to matter of a positron and an electron pair. And so the rest mass of a positron or an electron is 0.511 MeV. You have one of each. And so in order to create that, you have to have that much energy. Energy gets converted to matter, and you get the positron-electron pair coming out. This one is an interaction with the nucleus. So a high energy photon comes in, interacts with the nucleus, and an electron-positron pair is created from the energy of the photon directly to matter. So this electron and this positron were not there in the nucleus to begin with. They're not coming from the orbitals. They're just getting created by the photon. They come out with some amount of energy. They'll interact with other electrons as they come out. They'll slow down. The electron will slow down and get captured by an atom somewhere else, and the positron will get annihilated and give you 2 photons coming out, 0.511 MeV each, traveling 180 degrees apart from each other. Where is this useful?
PET scans.
PET scans. We're getting ready to replace our PET scanner in Mount Vernon. And it's important that they come out 180 degrees from each other, because then I can measure two photons, and I know that the positron was right here in the middle between the two photons. And that positron is a marker for a positron emitting nuclide, right? So, so a PET scanner doesn't get positrons from this pair production. It gets positrons from a nuclear material. It's going to be probably created in some type of generator, and that nuclear material gets swallowed and gets taken up by a tumor. But the positron annihilation is the same. So whether the positron comes from pair production or whether it comes from a radiopharmaceutical, either way, once it finally finds itself an electron to bond with, they annihilate each other, and two photons come out directly opposite at 180 degrees from each other. Yeah, it'd be interesting. It might be interesting to see what you see in a PET scanner with a high energy photon beam coming in. You could probably see your depth dose. You'd probably see the depth dose, right? Do a PET scan of a phantom with a high energy photon beam coming in, and your pair production will give you a nice picture on the PET CT of the depth dose of your beam. I don't know if anybody's ever done that, but it'd be interesting. Okay, what's it dependent on? It's dependent on energy. It's dependent on atomic number. How much? It's going to be directly dependent on energy, just linearly, so fairly weak dependence on energy, and then dependent on z as the log of z, which is even weaker than linear dependence. So it doesn't change too much above the threshold energy. There's the threshold energy, 1.02 MeV. You got to have at least that much to create a pair, electron-positron pair, and then it increases as you increase energy and increase Z. Okay. So when you put that all together, this is the fun graph that ties everything together. Your low energy X-rays, low energy photons primarily get photoelectric effect interactions. Your higher energy photons primarily get Compton interactions, and then as you get higher still, you start to get more pair production. And the sum of all of that is called the linear attenuation coefficient. And that's just a graph. That purple is a graph of the linear attenuation coefficient with energy. And then each of the individual attenuation coefficients. That's a good one to have in mind. It's probably, this is kind of the graph that sort of summarizes photon interactions, and so it's a good one to keep in mind. Relative importance. So these are just some hard numbers to go with the graph. In water, at different energies, what's the relative percent interaction, right? So low energies, you got photoelectric and a little bit of Compton. Higher energies, they might be 50-50, and that's at 26 keV. This is in water. These numbers would all change for a different material, but it's just, so this is just a kind of a general, well, just to put specific numbers to a specific case, but not a general rule. By the time you get to 150 keV, you're looking at a lot of Compton for water, right? Which that's one of your you probably have imaging beams that go up to 150 keV. So trick question. How come your 150 keV planar image or your 150 keV cone beam or CT scan, how come it doesn't look like crap? Because it's all Compton. And there's two reasons. You can put it in the chat if you're too scared to voice it. Here's a hint. Are all of the photons in your 150 keV imaging beam equal to 150 keV of energy?
No.
No. What's going on with the spectrum of your imaging beam?
So then the imaging beam does still have useful photon energy, and photons of useful energy.
Yeah, and the average energy, do you guys remember the rule of thumb there?
Yes, the average energy is about 1/3.
About 1/3. So 150 keV imaging beam is really more like this guy, right? More like 50 keV average. And you still got a bunch of photons that are going to be down here. It's a whole spectrum of energies, and so when you dial in 150 keV, that's actually just the maximum energy that you would ever see a photon coming out, but most of them are going to be less. So that's one of the reasons. And then the other reason is that this is these are numbers for water, and when you look at bone, those numbers are going to shift, right? Because it's heavily dependent on Z. And then this is another way to look at photoelectric Compton and pair production, but this is, instead of being against energy, this is against the Z of the material. So here you have the attenuation coefficient versus energy. Here you have the Z of the material versus energy. And so, like we said up here, right, this is for water. As you get up towards bone and metal and stuff like that, as the Z gets higher, the Compton effect, the photoelectric effect has a little more room to breathe. You get more photoelectric effect at higher energies for these higher Z materials. And similarly, pair production starts earlier at lower energies for higher Z materials. So the Compton effect gets squeezed as you get into the higher Z atoms. For lower Z, Compton is far more dominant. All right. And we're not going to do calculations, so I'm going to kind of skip over that. That's just a recapitulation of what we've already talked about. But just as an example, when you go ahead and calculate the Compton effect for a 90-degree scatter, you get, in general, you get a photon. So 90-degree scatter would be scatter off of your patient and into the secondary barrier, right? 0.511 MeV. So that's the energy of the photons that are hitting the secondary barrier after scattering off your patient. And then 0.255 MeV, which is half that. That's 180-degree scatter. Similarly, right, hitting the patient and bouncing back up to the ceiling. That's a primary barrier, so that's not as concerning. So this is the one we worry about for the shielding. So you guys aren't going to calculate this again, but that's just a reminder of why we care about Compton scatter for shielding. And okay, so that's photons. And now we're going to get to the compare and contrast part. We'll talk about charged particles. So there's kind of two different regimes, two different types of charged particle, and the only difference is mass. Electrons behave like other charged particles, but they're so light that it makes some fairly big differences to what they do in tissue. The two interactions of electrons and positrons are going to be Bremsstrahlung and characteristic X-rays. That's not counting the annihilation at the end of a positron's life, but those are kind of the two main ones. Bremsstrahlung is the braking radiation. It's where an electron is going to interact with a nucleus and the path of the electron gets bent. And as it gets bent, because it accelerates, it loses energy, and that energy comes out as a photon. This is what we're using to create our photon beams. So high energy electrons hit the target and then create photons. And this is where that direction of the photon emission matters, because if we're creating photons in an X-ray tube, we might use lower energy electrons, and that gives us a more of a isotropic emission of photons that kind of come out at every angle about the same. Whereas if we use high energy electrons, then we're going to get more like more forward. It's going to be, even at 4 MeV, it's pretty much all forward scattered. So that's the reason that your X-ray tubes have a 90-degree window. You're on an X-ray tube, your incident electrons come in this way, hit a target, and the imaging beam comes out this way. Can you guys see my cursor, by the way?
Yes, I can see the
forget
cursor.
I forget if you could or couldn't last year. Okay, so I'm not just gesticulating to myself. That's nice to hear. And then for an MV beam, you have to have a transmission target because the photons are coming out straight ahead. So you hit the target and photons come out in the same direction as the beam of electrons. Which is why for most of the accelerators you guys work with, you'll have an accelerator cavity that comes out horizontally, and then a bending magnet 270 degrees to bend your electron beam down, and then it hits the target and creates the photon beams, and that way the photon beams are also traveling down towards your patient. Anytime you where was I? Yeah. So the other electron interaction is going to be just a direct ionization. You'll get characteristic X-rays. And then when you kind of put those two together, this is sort of the spectrum of photons that comes off of a high energy electron beam. So this just kind of shows you the two interactions. So the Bremsstrahlung radiation, Bremsstrahlung photons are in this nice smooth curve. There's a whole spectrum of photons. It's just a random, well, not quite random, but a smooth distribution of photons anywhere from the maximum energy, which is equal to your highest electron energy, all the way down to almost zero. And then there's these peaks of extra radiation at the characteristic X-ray energies of whatever material you're bashing into. And then heavy charged particles interact a little differently. So instead of large changes of where was I? Instead of large changes in angle, right? Large angle scatter. A heavy charged particle is going to mostly just continue in a forward direction. It's going to bash into electrons, right? But a proton, when it bashes into an electron, hardly even feels it. It slows down a little bit, but it takes lots of interactions to slow a high energy proton all the way down to zero. And so it basically just goes in a straight line directly forward, interacts with a bunch of electrons, causes a bunch of ionizations. Every once in a while, it can interact with a nucleus, but that's not real likely. It's more likely to just interact with a bunch of electrons on its way to slowing down and stopping. The fun part is that as that proton, and we'll talk a little bit here in a second, but doesn't have to be a proton. It could be an alpha particle, which is just a helium nucleus. Could be anything heavier than that, and they're looking at carbon ions, right? Carbon nucleus, and a couple of others. as in addition to protons. Protons are kind of the workhorse of heavy charged particle radiation therapy, but there are other particles that are promising as well. So this applies to all the heavy charged particles, is that at the end of the particle's range, you get a really quick deposition of dose in a very short amount of time as it slows down. The way I kind of think about it is when you're coming to a stop and right at the very end, your brakes kind of grab and you get that jerk where all of a sudden you stop immediately. That's this Bragg peak. And the nice thing about a Bragg peak is you can deposit a bunch of dose deep in tissue without depositing a bunch of dose in the overlying tissue. And then the other thing that's nice about a Bragg peak is once you're done depositing all that dose, the particle stops and nothing else happens. So you get zero dose beyond. I mean, you almost couldn't design a particle for treating cancer that's better than that. I guess the only way it could be better is if you had zero dose in the overlying tissue, but I don't think that's physically possible. But this is really nice, really, really nice. And you can find that range very well. It's just directly dependent on energy and then how much stuff particle has to go through. So you get this nice dose. You get the nice sparing of healthy tissue above the tumor, a really high dose at the depth of the tumor, and then nothing beyond that. When a proton does interact, excuse me, first lecture of the year, I guess my voice isn't quite up to things yet. When a proton does interact with a nucleus, you get a bunch of other really high LET interactions that might enhance cell kill a little bit. So proton beams are have a little higher biological effect. So that's kind of a comparison of protons versus photons, right? If your tumor is here, then this is all this stuff from the photon beam is not just wasted, it's detrimental, right? It's damaging healthy tissue far more than it's killing tumor by a factor of maybe 2 to 1, right? This might be 50% dose, 100% dose here in healthy tissue that you're not even targeting. And so you have to do all kinds of funky things like 7 or 8 beams or full arc rotation to try and spread out this stuff that you don't want in favor of this stuff that you do want. Whereas protons kind of give it to you from the get-go. Now, unfortunately, most of your tumors probably are not this size. So you do have to back things off a little bit and spread that Bragg peak out. And so instead of having a nice sharp dose deposition, you're going to have to spread out that Bragg peak to the depth of the thickness of your tumor, right? And when you do that, you lose some of the surface sparing. Fortunately, you can get around that by using a scanning beam. We'll talk about that later, but this is kind of the early, not even early, this is sort of the state of the art right now. The scanning beams are more the future, although they really are kind of coming into their own right now. Does anybody get to work on proton planning right now? Nobody? That's too bad. I guess that's another question I had for COVID. Are you guys allowed in the center for your clinicals these days? Have they backed off on some of the?
Yeah, I think we're all allowed in.
Okay.
Well, I work where I do my clinicals, so yeah, I'm allowed in.
Okay. Yeah, I know for a time they didn't want students in the clinic because it wasn't medically necessary and you guys were second-class citizens, but hopefully that's not quite so bad these days. Okay. So that's most of, I mean, this is just an overview. We'll get into electrons and protons in much more depth, but yeah, so let me just finish up here. So we've got, like I said earlier, a couple of other types of heavy ions are being used and tested clinically, but protons are still kind of the workhorse there. And as you go to heavier and heavier ions, you get an even more pronounced Bragg peak. And so all the stuff we talked about for protons is just magnified as you get heavier ions. The only thing is to get a helium nucleus, alpha particle, or an argon nucleus to penetrate tissue, it has to be exceptionally high energy. And that gets kind of difficult to do. Neutrons, we're going to try. I still don't have a real good feel for the pacing of this course yet. So we're going to try and do a little bit with neutrons. If we don't get to it, I won't be too sad just because electrons are kind of, sorry, neutrons. Neutrons are kind of yesterday's news. There might still be a few centers using neutrons, but really it's not going to be a real commonplace thing for you guys to see, and it's probably going to be less and less common as we move towards the future. But just to compare those to all the other particles we've just talked about, neutrons are indirectly ionizing because they don't have charge, and so they can't interact directly with the electrons and cause an ionization. And so what they end up doing is they bash into a hydrogen atom, which has pretty much the same mass as a neutron, and that will slow them down pretty well. And then that hydrogen atom can then go on and cause an ionization, or they might get absorbed by a boron nucleus, which is good at absorbing neutrons, and then it will then decay. And so we care about neutrons. It is used in therapy, like I said, but not real common, and kind of becoming less common. But we care about neutrons because they're hard to shield. And so a lot of times for your high energy photon beams can create or they can knock loose electrons off of stuff that the beam is incident on. And those neutrons come out and they're difficult to shield. And so it's something that we have to take into account when we're shielding your your vaults. So they're heavy, they're neutral, they can only interact with a nucleus. They have to have something to bash into. And when they hit into a nucleus, just like when a proton hits into a nucleus, which is, you have this high biological effectiveness because lots of energy gets deposited in a small area. And our target, that DNA, is a pretty small thing. So if you have lots of energy in a small area, that's effective at creating the double strand breaks in the DNA that kills off a cell. So ends up being fairly high biological effectiveness. But the PDD, the depth dose, is similar to an X-ray. So it's not nice. It doesn't have the nice Bragg peak like a heavy charge particle does. In fact, a neutron depth dose looks a whole lot like a photon depth dose. Almost, I mean, you couldn't, if I just gave you a depth dose, you wouldn't be able to tell the difference. So yeah, so that's that. Hopefully that was somewhat productive. The rest of the course, I'm not going to be just a wall of lecture. There'll be more interactive. We'll be doing calculations and stuff. So hopefully, if you made it through this class, then you won't need caffeine for the rest of them. Hopefully. All right. So let's see. Let me just bring up. Stop. Let me just bring up course. Okay, so there's a survey. This is about your clinical electron hand calcs. Now, most of you probably don't do electron hand calcs on a regular basis, but hopefully your physicist or your dosimetry department has either a spreadsheet or a worksheet that they use to do electron hand calcs for, every once in a while if you do a clinical electron setup or something like that. And so these are just some questions that I want you guys to go research from your clinic, and then we'll kind of talk about the different ways that your different clinics are calculating electrons for hand calcs. And then TG71 is the AAPM task group that goes over monitor unit calculations. And so I just want you to read through that. There's the task group report and there's a quiz. It's all conceptual. I'm not having you do calculations until after I actually go over calculations next time. There's the syllabus. Hopefully it's reasonably understandable. If you have any questions about what's in the syllabus or concerns, let me know. And there's the PowerPoint that we just went through. We'll start in on electron hand calcs next time. Any questions before we adjourn? Oh, I wanted to mention due dates. So currently I have October. I have both of those assignments due Tuesday at midnight, so midnight the night before next lecture. Is that a decent assignment schedule, due date schedule for you guys?
I was gonna ask if that electron one can be pushed back just like until Thursday. I'm not in. I already had my 3 days at clinic this week, so I'm not in my clinic anymore this week. And then I work Monday, Tuesday at another clinic, and so Wednesday is the soonest I could get the electron information.
Okay. Yeah, let's see. Then maybe I'll just do have the survey due here. Because I mean we'll be doing electron calcs for the next couple of weeks, so maybe I'll just bump that to the 12th.
Thank you so much.
Yep. Any other questions, concerns?
No, glad to have you back.
All right, well, it's good to be back. We'll see if we can see if we can get through a new class.
It looks like there's a question in the meeting chat.
Oh, I don't see it. Am I looking at the wrong chat? Let's see.
It was me. I just don't have very good service to talk. I don't know if you can hear me.
Yeah.
I was asking if the final was comprehensive.
Yes, the final will be comprehensive.
Okay, thank you.
Yeah, I'm wondering why I don't see the chat. I have the chat window open. I don't know. Can someone else just type a test chat in there and see if I can see it? I don't think there's any other chat window that I can have open.
Type test.
I could see that, Victoria. I could see it coming up fine.
All right. I will have to figure out what's going on there. Well, okay. So just so you know, it might be that I can't see your chats for some reason. I'm not sure why. Let me open it back up. Share conversation. Yeah, I'm not getting. I'm not getting them. Well, we will remind me to test that at the beginning of next lecture, and then hopefully we'll get that sorted out. Now, when you here, let's see. Can you see mine?
Yeah. My meeting chat, the whole side is the same, is the darker screen, whereas yours is the white screen. I don't know if that matters.
Yeah, I don't know either. I didn't have trouble with this last time. It worked just fine. All right, well, I have to figure that out. Okay, last thing. I will post these up on YouTube as long as that's okay with everybody else. I figured out last year that I don't have enough storage space to post them on Canvas, and so that's why we ended up switching over to YouTube. So I'll just do that from the get-go here this time for any of you that want to listen to this over and over and over again.
Brian, can you resend a link to that?
Yeah, I'll put the links up on Canvas as I get them. I have to download them and then upload them to YouTube. And once I get them uploaded, I'll put a link. So it should show up on the Canvas modules. So I'll just link them in each of the respective modules that they are associated with. Okay. All right, then I guess we are done. I'll see you guys next time.
Thank you.
Thank
Night,
you,
everyone.
Brian. Have a good week, everyone.
Yep. See you guys later.